It's Donut Friday in the office. So I'm gonna eat a donut and explain a paper to you. So the plan is we're basically gonna talk about all of the concepts that are inherent in this title. So what is SVD? Which transformer weight matrices? And what do we mean by highly interpretable? Okay, cool, let's begin. So when I think about a transformer, I think about this picture. It's basically a neural network architecture that revolves around this central object called the residual stream. Now, if you have this in mind, then we're good to go. When we look a bit deeper, what I mean by transformer is this. So we have some input tokens. This is basically like a sentence that we tokenize into like discrete chunks. We embed this to get like vectors corresponding to each of our tokens. And then we basically have multiple vectors corresponding to each of the input tokens in our residual stream. So our residual stream is made up of one vector per input token. What happens then with this residual stream that is denoted as x0 here at the 0th layer, we feed it in to a bunch of these attention heads. I'm going to talk about what they do in a bit more detail soon. And then after we do the computation of these attention heads, we basically add them together and put them back into our residual stream. After that, we feed the residual stream into a multi-layer perceptron, which is just a standard neural network, and then feed the result of that back in. Now, all of this here is what we call a residual layer. And then at the very end, the kind of final layer, we use this thing called the unembedding. What the unembedding does is it takes this residual stream, maps it back into what we call token space to get the logits. The logits are just like real numbers. And then we look at the highest real number to see what the transformer predicts is the next token. So now that we know we have these like multiple residual layers, I want to introduce one of the key thoughts that we need in order to understand the paper that we're presenting. The key insight I want to drive your attention to is the insight presented in a blog post on Less Wrong called the logit lens. So this work appeared a couple of years ago and has been used in transformer interpretability work. We've seen that we have these residual layers. Instead of performing the unembedding after the last layer, we can perform the unembedding on any of the residual layers. Okay, so if you back up for a second, what we'd expect as we feed our input tokens through the residual stream and the information travels is that at the end, when we do the unembedding, we get the prediction of the model of the next best token. But what can happen here is that we can actually see what the model is currently thinking, what the next best token is. In that case, you can kind of think of the residual stream as an accumulation of information. And so it makes sense that we could extract at some intermediate layer what the neural network is actually thinking is the most likely token. And that's the main insight behind what is known as the logit lens. Cool. Now we've seen how the transformer looks like. So now I basically want to draw your attention to the matrices that we want to interpret. So let's start with the MLP here. The MLP basically looks like a multi-layer neural network. It has one hidden layer and one output layer and one input layer. And the two matrices that are associated with any MLP are the WIN, which is the weight matrix that takes the input and maps it onto the hidden dimension, and WOUT, the weight matrix that maps it back from the hidden dimension to the output dimension. Cool. The other matrices that we want to interpret are hidden here in these attention heads. To understand which matrices can be interpreted, we need to have a better understanding of the attention mechanism. So this is basically how it looks like. What we do here now is we have a value, key, and query. Those are actually the embedding vectors of the token, and to create the actual values, keys, and queries, we multiply them with the respective matrices. So to obtain the value matrix, we multiply our input token with this WV, the weight matrix, to create the values. Similarly here we have WK and WQ. And then we perform what's called the scaled dot product attention that you can see on the left. And you concatenate the results because this is multiple heads, but don't worry about that. And then we have some sort of output matrix that writes the results back into the residual stream. Okay, so one thing I want to draw your attention to is that the key and query matrices are basically matrix multiplied, scaled, masked, and softmaxed. And all of this happens only on these two. But the value matrix goes right into this matrix multiplication here with the query and key. And through there, it has this direct path that I drew in here with orange with the WO matrix. And so WV gets multiplied through with WO. And that's what we call the OV circuit. To be a bit more precise, we can also look at this diagram, which kind of shows the operations involved in the OV circuit. And so here you can see that we first embed our token, we multiply it with the vector that creates our value vector, then we multiply it with the output matrix, and then with the unembedding matrix. So embedding, value, output, and unembedding. And so here in brown, you can basically see this OV circuit. Okay, cool. So we've talked about how the transformer works and which matrices we would like to decompose. Now, the other crucial thing we need to understand is singular value decomposition. Just as a brief kind of introduction, we can think of single value decomposition as doing the following. We have a matrix, the M. We can apply our linear transformation M, and so our standard basis vectors will just be like shifted by a bit. We can also equally well just like decompose this, and this is what SVD is telling us, into a rotation, a scaling, and another rotation matrix. And so the wonderful thing about SVD is that we can decompose any rectangular matrix into its left singular vectors, the singular values, and the right singular vectors. Pictorially, this all looks like so. We have a rectangular matrix of the size mxn, then we have a matrix U of the size m by n that has all of the left singular vectors in it. We have a diagonal matrix sigma that contains all of the singular values on the diagonal. And we have V transpose, which contains the right singular vectors. Another interesting way of looking at SVD is the following, where we can take this pictorial view and describe any matrix M by a sum over its singular values times the outer product of the left singular vector and the right singular vector corresponding to the singular value. You can basically think of it this way. The singular value matrix contains the most important singular values on the far top left corner, and then on its diagonal it's going to have decreasing singular values in importance. And so what happens here, you could basically choose to reconstruct your matrix M with the first singular value and its corresponding singular vectors. In essence, what SVD is telling us is that we can decompose a matrix into a linear combination of right and left singular vectors, scaled by their corresponding singular values. And this leads to quite an interesting application where we can basically identify directions in our matrix and edit them out. So if we wanted to, say, remove the first singular vector, we can simply do so by taking our original matrix and removing the matrix that corresponds to this term. To drive this point home, let's look at the SVD projection method that the authors propose in their paper. As an example, we can take the OV circuit and apply SVD to it. Okay, so if we apply SVD to our OV circuit, we'll basically obtain these three matrices again. And now we can, for example, take this right singular vector and try to interpret it. What I mean by try to interpret this is basically just applying the unembedding matrix and seeing what the transformer currently thinks. Applying this unembedding matrix will give us the logits, which are of the size of the vocabulary. And this will basically look like so. Now with these logits, we can basically take the top K, let's say top 10 logits, and try to see what the model actually is thinking at this point. And so here's one of the main findings of the paper, where they structured this table in the following way. We're looking at the singular directions to the right, and then the rows correspond to the top K tokens. So as you can see here, the tokens that correspond to the second singular direction are basically all very tightly clustered around this concept of writing, writes, written, wrote, letters. We can see that this direction corresponds to writing. So this is one of the main findings of the paper, and with that we can go to a discussion of what we actually think about this paper. Okay, so let me just introduce like the main idea here. So what we want to do today is just talk about this paper that we found interesting, which is called "The Singular Value Decompositions of Transformer Weight Matrices Are Highly Interpretable." And this format is basically us kind of going through the paper together, explaining the key ideas, why we thought it's interesting, what its relevancy to AI safety is, and how we think about maybe extending this stuff, and yeah, whether we think the methodology they employed is sound, what it's missing, and what maybe is good. Does that sound about right to you? Or do
Yeah,
you
that
have
was
any
great.
other goals? Okay, cool. Great. So let's first start perhaps with like the overview. So can you tell me a bit about like what this paper signifies for you and what the main contribution is?
Yes, so the paper proposes a way to look at certain weight matrices inside the transformer and tell us something about what they're doing. And in particular, it looks at the singular value decompositions of these weight matrices and uses like the directions these correspond to, the singular vectors correspond to in embedding space to like understand what the model components are doing. And this is good because we would like to understand what each model component is doing in order to eventually be able to completely understand what neural networks are doing inside and be able to, for instance, edit them or notice if they're doing something we don't like. Yeah, and I don't think anyone else had done quite this, had like approached it quite this way before. People had done stuff like their SVD or non-negative matrix factorization on activations, as far as I know. For instance, the DeepMind AlphaZero interpretability paper used NMF on activations, but this paper uses SVD on weight matrices instead, which, as far as I know, hadn't been done before for transformers.
Mm-hmm. Okay, cool. And so wait, well, what you're saying is that we haven't applied any like linear algebra methods yet to transformer weight matrices. Is that correct? And that's the kind of first instance that tried this very sensible idea.
As far as I know, yes, though I could just not be aware of something. I'm definitely aware of like previous work using linear algebra methods on transformer activations. Like there is this blog post by Ammar called Interfaces for Explaining Transformer Models. Interfaces for Explaining Transformer Language Model, where he uses non-negative matrix factorizations on activations and has some nice visualizations. But yes, as far as I know, like I don't know of any other work before this which had done it for weight matrices.
Okay, cool. Now, another high-level question before we like dig into the key concepts. What do you think is like the relevancy for AI safety here, and how much of a step in the right direction do you think this signifies?
I think it gets us a little bit closer to understanding what models are doing. It like helps us locate model components which, well, hopefully, if it works, it helps us locate model components which deal with particular kinds of things. Like maybe we can figure out which attention heads are doing something to do with entertainment or something to do with like some other semantic category like sports or something. And then this might help us understand the computation eventually, like possibly all the computation that the transformer model is doing, like in the good outcome, which if we could understand all of the computation would be quite helpful, just to ensure that the model is not doing something we don't want it to be doing. And also maybe to like, in a microscope AI way, learn like what a superhuman model is doing to do tasks well, and then just learn something about the domain using that. That's another way in which like really understanding what models are doing could be helpful. And also we could, if we had a very detailed understanding of what the model is mechanistically, what algorithms are implemented in the model, perhaps we could also edit these algorithms to like remove certain components which are dangerous, for example. And it might be quite helpful then to be able to locate the dangerous components inside a model. And like this work contributes to this, makes a small step towards being able to do this, I think.
Mm-hmm. When you say you want to be able to interpret the computation that the neural network is doing, can you tell us how, like, when we look at activations versus weights, how our interpretation differs and how these impact the kind of computations that the neural network is doing?
Yeah, so I think a good analogy to have in mind for understanding the difference between interpreting activations and interpreting weights is that activations sort of correspond to like the concepts you have in mind. The activations on an input are sort of like capture the concepts you have in mind while thinking about something. So if you can interpret activations, you can hopefully understand what kind of concepts a model is using while thinking about a particular input. Whereas interpreting weights is more about like understanding the entire like mental architecture, like all the algorithms implemented, or like all the circuits implemented inside a model, like the model's whole algorithm for doing things. Which one like difference is that you could be quite like you might be able to understand when interpreting activations, it might be sort of easier to understand all the concepts you have in mind for one particular kind of input, or like maybe just identify a few concepts from the activations. Whereas like in the case of interpreting weights, well, if you like fully understand all the weight matrices and how they like come together to make up the computation of the model, then you've just like fully understood the entire like all the algorithms the model that are implemented inside a model. Like you fully understand the mind, you fully understand the mind of a model, as opposed to in the case of activations, just like understanding the concepts you have in that you're thinking about when analyzing a particular input. In the case of activations, you could like in principle, like I think understand all of the features of a model without understanding how the features like link up. Like you might not understand the algorithm which computes the concepts it's thinking about inside layer L, like the concepts it's tracking inside layer L, with the concepts it's tracking inside layer L+1. Like you might understand all of these concepts, but you don't necessarily understand all of the like the way it computes the next layer's concepts from the current layer if you just understand activations. But if you understand weights, you've like basically understood everything, I think.
Okay, so let me try and summarize the intuition you just outlined. In effect, when we look at activations and we decompose them, we hope to find some interpretable features along the lines of, well, here's a dog nose detector, this is flappy ear detector and whatnot, right? And in that sense, we hope to find like human understandable concepts that the model uses while interpreting the input it's being given. But the way it does that is encoded in the weights. And so when you say algorithm, what I'm thinking about is, well, something like the IOI had, the indirect object identification had, where it is just like a fact about the world that transformers can finish the sentence, John and Mary went to the shop and like John bought ice cream for, and then you know the transformer is able to like look back and be like, hey, which name was already, did I already see? Or like, no, actually, yeah, the thing the IOI had is implementing is a bunch of different things. One thing is looking at whether a name got repeated already, then looking at the name that was not repeated, and then basically filling out the blank at the end of the sentence with the name that hasn't been repeated yet, right?
Yep.
And that, I think, in the intuition that you outlined is the algorithm,
Yeah.
But then the concepts that are being used, like for example, John is a name, that is something that we would expect to find in the activations rather than in the weight matrices.
Yeah, in some sense, all the like concepts it has to be thinking about have to like somehow be created by mapping through a bunch of weight matrices. So in some sense, like the concepts have to be also present in the weight matrices. It's maybe sometimes simpler to get the concepts from the activations, but also it's like maybe from the activations we can just get the concepts and not understand how the concepts are computed on an input. For the concept of friend to be implemented, some of the connections have to capture something about like computing whether someone is your friend. So in some sense, the concept of friend is also captured in the weight matrices. However, it might be easier to determine that it's a concept if you're looking at the activations than if you're looking at the weights. But also, like on the other hand, just by finding that, oh, inside the activations, there is a friend concept, you won't really understand necessarily how the friend concept is computed by the network. So it might be easier to find the concepts from looking at activations, but you're also like more restricted in that you'll possibly only find what the concepts are and not how they are computed. The basic TLDR is activation analysis is about finding concepts, and weight analysis is about understanding how things are computed, in particular, how concepts are computed.
I guess what I want to talk about next is kind of the key concepts that are necessary to understand this paper. And when we spoke a bit about decomposing activations and matrices now, or like weights, the question then is in specific, what weights? And you mentioned circuits a bunch. Perhaps you can like give a brief explainer of what a circuit is, and then also like which ones we want to look at.
So mostly by circuit, I just meant like a small subset of the model components which computes a particular task. And it at least seems like if you look at some smallish language models like GPT-2, you can find for particular tasks circuits which specialize to doing that particular task, like the indirect object identification task we talked about earlier. So in that sense, by a circuit, I just mean a subset of the model which is responsible for doing a particular task. And like hopefully we can understand how it does the task exactly as well. Like a very simple example would be an induction head. For example, you might have a sentence which is like, Mrs. Jones went to work. After that, Mrs. and then your model has to complete the next word. And most likely the next word should be Jones. And how does a model do that? Well, basically it looks for like the previous instance of Mrs. and then something, and then just copies the something that came after Mrs. This is like sort of like an instance of applying induction. So that's why it's called an induction head. The mechanism, which usually is learned for doing this, is that for every token, you have a head which moves the previous token information onto that token position. So in the first instance of Mrs. Jones in the sentence, the information about the previous token being Mrs. is moved onto Jones. And then you have another further attention head down the line, which when your query is Mrs., it looks for Mrs. being represented in this previous token subspace. And then it finds Mrs. at Jones. So the key at Jones is Mrs., like corresponds to I am storing Mrs. here. And then it finds a match between this Mrs. stored at Jones and this Mrs. later. And then once it finds a match, it like copies the value from the position of Jones, and the value there for this head is just the information that the token there is Jones. And now if you combine these two heads in sequence, you've now been able to like copy the information that previously Mrs. was succeeded by Jones onto the next Mrs. position. And then the model knows to predict Jones at that position in the residual stream. So that's the simplest non-trivial example of a circuit that I know of. I think it's from the mathematical framework paper by Anthropic.
So there's a specific notion in which like the OV circuit is just the matrix that we multiply our residual stream with to obtain our value matrix, right? And this weight matrix is the WV matrix. And then we multiply the V matrix with our output matrix that writes back into the residual stream, which is the WO matrix. And then this WV times WO, this is the OV circuit, right? And I mean, this is like one particular instance of a small circuit, but we can basically compose these circuits over multiple layers. And that's where we expect like interesting behavior to crop up. And for example, something like the IOI head is impossible in like a one layer attention transformer because it doesn't have the right circuit to do the task.
I guess yes, like this is also a circuit, but I think it's in a somewhat different sense than the circuits used to do particular tasks, at least to me, or like maybe I'm just missing some connection, but like the circuits used to do particular tasks are like everything in the model which explains like how it does this one thing it can do. Whereas like the OV circuit is just sort of like a useful like pair of model components to think about together. And then this can be combined with other stuff to make potentially this can like appear as a subpart in other circuits. But I guess it's like also reasonable to call parts of the model which do things and which are like useful to think about as doing things together, like circuits. But it seems like it's just somewhat something of a distinct use of the word to me. Yeah.
Okay, cool. So let me see. I think what's important here is also to understand why the authors kind of apply this SVD methodology to only the OV circuits and the in and output matrices of the MLP layer, but not the QK circuits. Would you mind like speaking a bit to that?
Yeah, so I think the reason they give in the paper is that they think that QK circuits are much more syntactic, and the information like embedding space directions correspond to semantic things. And if you do an SVD on, for example, the OV matrix, or if you do an SVD on the MLP's input or output weight matrices, you're going to find some directions which live in embedding space, and the embedding space directions just are semantic. So if you have a model component which does something syntactic, it's not that likely that like the direction in a fundamentally more semantic space would be meaningful.
To summarize, which do you expect to happen where? So the OV circuits you expect to capture semantic information, and the QK circuits you expect to capture syntactic information. And what we are after are concepts, and so we want to look at the semantic meaning of the computations, and that's why we look at the OV circuits and not the QK circuits.
Yeah, I'd say something like we're looking for semantic. This method lets us identify semantic aspects of what the model component is doing, because embedding space sort of naturally captures semantic aspects, it seems like. And the directions we find are in embedding space. So they sort of have to end up being semantic directions. And therefore, like, if a model component is more about syntax, we're going to have a hard time interpreting its directions. Something along those lines. I don't think it's like a fully rigorous mathematical argument, but I think there's some like correct intuition in this argument about why the OV circuits end up being more interpretable in the sense of this method.
Okay, cool. I think one other key thing that we still need to talk about before like looking at the actual method of the results is like the idea behind logit-lens and the main insight that was proposed therein.
Yep. So logit-lens is a cool piece of work from Nostalgia Based, posted on Less Wrong a few years ago, which has now been used in lots of papers. And the idea is that like if you just look at the residual stream dimension, then it's just the same for every layer. So you can like the math allows you to unembed at every layer, unembed back from the residual stream into like token space. And then you can just see at this point in the residual stream, like halfway through the transformer, if I unembed, which tokens get high probabilities. And the thought is that this captures sort of, if I had to stop my computation midway through transformer, what would I answer if I had to answer now? Now, I don't think this like, again, quite makes sense rigorously, because like the transformer was never trained in an environment where it had to stop like the computation midway through in exactly this way. There's like a few issues here. Like one is, why would the space in residual stream after layer 5 even match up with the residual stream after the last layer, which is actually the one used for the unembedding? And also, like, why couldn't it be that just in the intermediate layers, it just stores some like intermediate information which doesn't have to do with its guess for the output right now? But like, despite these concerns about it making sense in theory, it sure does seem to do like cool stuff in practice. I don't remember if this is exactly an example from the original post, but the like flavor thing that you can see with LogicLens is something like, if you have the first sentence being, the following sentence is incorrect, and then the second sentence is 2 + 2 = blank, then I think the type of thing you see with LogicLens is that first, in the early layers, it says 2 + 2 = 4. And then when it gets further in the computation and sees, oh, the last sentence wants me to answer incorrectly, the answer turns to some other number, like 5 instead of 4. At least empirically, it looks like it does first apply some like simple patterns, and then it like applies the higher level, like more complicated patterns later to like change its answer to its eventual answer. And then you can sort of track like what stuff is it doing in every layer. Yeah. So the idea of the LogicLens is to like connect the residual stream at every layer with the token space.
Yeah, I think also if we like look at this, it's, as you point out, this is not like rigorous, and we wouldn't expect this to happen. But after we've done it and like have seen these results, it kind of nicely tells the story of the residual stream as like an accumulation of knowledge. We kind of read from it and perform like attention or the multi-layer perceptron on it, and then we write back into it, right? And so in some sense, the residual stream is like the central object of the transformer, where you have information flowing out and in again and out and in. And so it kind of accumulates more and more evidence about the world, so to say, and uses that later to like make its prediction. But at every intermediate step, it's like refining its guess, so to say, as to which token to predict next.
Yeah, that's a good way to put it. Yeah.
Okay. Nice. I think those are like the main kind of intuitions here. Yeah, let's talk a bit more about their method then and what exactly they do. So something they have in their paper is called SVD tracing, with which they locate the semantics kind of with natural language prompts. Can you like specify what that means and how this method works? Potentially you can like draw this out.
Yeah, sounds great. Yeah. So for every singular vector of your OV matrix, for example, you can compare it with the vector you get when you embed this token into the residual stream. And the way you can compare them is just, for instance, you can look at the angle or the cosine of the angle. And then if the cosine of the angle is high, then the vectors are similar, like the vectors are in roughly the same direction. If the cosine is 1, then they're exactly in the same direction. And also if the cosine is very low, then since singular vectors are only defined up to multiplication by -1, like you can switch the sign of both a left singular vector and the corresponding right singular vector at the same time. And that doesn't, like, that's also a valid SVD decomposition of the matrix. You also want to look at like singular vectors which give very low dot product, so which have angle which is very close to 180 degrees instead of very close to 0. Yeah. So
okay, let me quickly try and understand this. So what we mean by query here is like, let's say we have a concept that we want to probe for. Let's say we want something that clusters around fire, flame, and hot or whatever. And so we like take these we embed them, and that gives us our x hat. And then we like look at all of the different layers and hats, or like layers and hats, and then also the weight matrices of our MLP layers, and we like take the singular value decomposition and look at all of the like singular vectors that we get, either from the left or the right singular vector, and compare them with the embedding that we got from embedding these like semantically close ideas like fire, flame, and hot. And hopefully we'll just like identify the one singular dimensional, like a couple that like activate highly or like point in a similar direction as the concept that we're looking for. And then, we kind of know where to locate the concept within our transformer.
Yep, that's exactly right. Yeah. So in your example, the Q vector here would be for like the fire, flame, and hot example, this Q vector would be a huge number of zeros, like 50,000 minus 3 zeros, and then 3 ones at fire, flame, and hot. And then this QE is just summing up the embeddings of fire, flame, and hot. And then you get like some sort of residual stream vector, which captures all of fire, flame, and hot. And then you want to see like which model components, as you said, attend to this direction. And to find this, you look at these angles between the singular vectors of particular weight matrices and this fire, flame, hot vector you constructed.
I see. Okay, cool. And then how do we interpret the graph that we're looking at with the missing x-axis?
Yeah, so I guess they're looking at one particular layer in a transformer, looking at all attention heads in this layer. And I think the x-axis should be, I'm guessing, singular vectors ranked according to the singular values. And then it also doesn't have a color code, but we are guessing that this yellow and darker shades probably are to say that this yellow thing is a very high dot product, a very high cosine of the angle between them. So they're in very similar directions, and probably the violet ones are like very dissimilar. So meaning that like they're in opposite directions roughly. The plot doesn't have an explanation of what the colors mean, but I think one very reasonable guess is that the usual bluish shade here just means that the dot product, or the angle between your embedding vector and the singular vector, is very close to being 90 degrees. They're very close to being orthogonal. The cosine is very close to being 0. Whereas this yellow color plausibly means that the cosine is close to being 1, and this dark like violet color here means that the cosine is very close to being -1. So these respectively mean that the vectors are either in basically the same direction or basically the opposite directions. But since SVD directions are only defined up to ±1, this should all like be interpreted as meaning the same stuff, which is that like the SVD direction cares about this embedding vector. These 3 places here are the places where we see singular vectors which care about this particular embedding vector. And I guess the fact that you get like just 3 things here instead of like a plot which has uniform coloring roughly, I guess tells us something about maybe this capturing something real. Though actually I'm not sure. They don't quite explain. They say that they set the threshold to 0.15. So maybe everything which has this uniform shade here is just less than 0.15 in absolute value of the cosine of the angle. In which case, I guess it's not that the plot itself is not that strong evidence that there's something crisp going on here, where some singular vectors really care about this direction and some don't care at all. Like maybe they just plotted it this way. I guess it's unfortunate they don't explain how they generated this plot.
Yeah, that that is interesting. They could also just have cherry picked it, right? And
yeah,
the plot might have looked much more like a proper heat map.
Yeah.
That's like very random. Okay, yeah, let's see. Can you speak to how this is different to the other method that they use to identify directions? This SVD projection method.
Yeah, so that's like a different kind of thing to me. Like here they're analyzing the SVD directions, whereas in that case they're like looking at the particular token or a particular set of tokens and asking which SVD directions correspond to most to these. So it's more about like finding the model components which correspond to a particular input. Whereas this is like asking the opposite question of like, if I have a model component, can I say which inputs does it correspond to?
Okay, yeah, that makes sense. Can you zoom in on that plot and like basically explain what we're seeing? We have the singular direction from left to right, and then the top K tokens, right, on which each of these directions activates. And then, you know, if you look at the second direction, we can like kind of see that it activates on very tightly clustered concepts like write, writing, writes, written, wrote, letters, and stuff like this, right? And this like broadly holds true for other OV circuits and also for a other singular directions. So if you look at the second or third singular direction, we still have like quite interpretable clusters.
Yeah, so the thing they precisely do here is they take each of the singular vectors of this model weight matrix, and then they unembed them, getting something in token space back, and they just look at the tokens which then got the highest values at the corresponding indices of the unembed vector. If you were to unembed this singular vector, like what would the immediate predictions of the transformer be? Like which are the most likely tokens predicted? Yeah, and this is like sort of analogous to the logic lens idea that like basically just feel free to unembed everything inside a transformer and you get something which is roughly interpretable, hopefully, out.
Yeah, that makes sense. When I look at this, I'm like, okay, that's great. And like, yeah, I can see that this is interpretable, but how sure can I be that, you know, this is interpretable for all of the other heads, like other weight matrices that I'm gonna decompose? I think in the paper they use two different methodologies to do the labeling, one of which is, you know, just like manual labeling, and the other one is automated. I wonder what you think about their labeling strategies and whether you think there's like a scalable approach to doing this.
Yeah, so what they do is just like look at this list of words, I think, and then just try to like, from intuition, say, does this list correspond to something interpretable or does it not correspond to something interpretable? And do you remember if they also like try to explain what it means actually? Like, do they have to write down the like meaning in words of this direction?
I don't think so, but
Okay.
what I like is that if you go to the section manual labeling of GPT-2 Medium,
Yeah,
you will find a fun calculation of like how many hours in human labor it took to do the labeling, which is like mind-boggling, but it like shows quite neatly that this is not scalable and that we need like another solution, right? They say that it took them like 6 hours of focused work, right, to do 40 singular directions in 24 MLP blocks, but it would have taken them significantly more to just like finish GPT-2 XL's 48 layers and 25 heads. And they estimate that at their rate, it would have been like 330 hours, which is just like, you know, you don't want to pay a researcher to do this manual type of work. And so, yeah, what they propose is like a way of automating this with GPT-3. Mind you, back then, you know, they didn't have access to GPT-4 and they ran into a bunch of like small side issues that you might not have with GPT-4 anymore if you wanted to do this labeling, which actually reminds me of this one paper. Perhaps you can speak to this as well, but like there was a recent paper on like interpreting neurons in GPT-2 with GPT-4.
Yeah, so maybe I'll first say what the method here is here to contrast it with the OpenAI paper. So what they do here is just basically asking the model to do the task that humans are doing. So the human task is figuring out whether some set of words has something in common. Like, for example, what do all of these words have in common, like the, and, a, in, and the answer is most of these words are prepositions. So whereas for other lists of words, like there might be some directions which are not interpretable. Like for instance, this list of words, past, oaths, properties, blem, coins, ensign, iliate, and so on. Like plausibly it just doesn't have a shared semantic meaning.
Oh, those are just like all of my favorite items.
They have
How does it know?
yeah, they're very meaningful for you. So basically, I think what they do is they give the model a few shot prompts where they give a bunch of examples of the kind of like threshold that they want to have, which makes this thing here have something in common, whereas this list here does not have something in common. And they ask the model to answer the same question for things which they haven't manually labeled yet. And they use this to automate this interpretable versus not interpretable labeling process. Yeah, and then they also have this way to check the consistency of the answer proposed by the model later.
I think
Yeah,
this is
and
basically asking GPT-3 to like critique itself, right? And
yeah,
like looking at its own outputs and being like, wait, given this list and the label you produced, I'm not quite sure this is like very well done. Or yes, this checks out, this is great.
yep, exactly. And then they eventually say that the direction is interpretable if the model proposes an interpretation to it, and then the verifier also says that yes, this interpretation makes sense. And the verifier again has a few shot prompts to help it.
Can we briefly look at the results? Can you zoom in a little? What are we looking at here?
I think these are the MLPs, the in and out weight matrices, and it plots the fraction of all the SVD directions which are interpretable. I wonder if they only looked at the top sum number of SVD directions, not like all 700 of them. Maybe that's not so important to figure out. But yeah, so anyway, they're plotting the layer on the x-axis versus the fraction of directions interpretable for the MLP in that layer. And something that can generally be seen here, I think, is that it tends to go up as you go into later layers. And it's sort of unclear if this like has to do with just being closer to the output. So maybe like you have to orient in the human like semantic space more instead of some weird like intermediate concept space. Or maybe it's more that like the intermediate layer residual streams are more out of sync with the output layer because of like there not being any technical guarantee that they have to represent things the same way. The residual connections, of course, enforce some amount of this, but like it's not like completely rigorous that it has to represent things in the same way as the last layer. So maybe it's just more being more out of sync with the unembed that causes this. I think they like look into this a bit in the tuned lens paper, and their answer is that basically tuned lens doesn't make this behavior go away, but I don't remember the exact details. It's in one of the appendices of the tuned lens paper. Yeah, let's now compare this with the OpenAI paper where they use GPT-4 to label MLP neurons in GPT-2. Yeah, so the way they use GPT-4, I think, to interpret neurons is very, very similar to what conjecture did, which causes me to be somewhat confused about people being super excited about this because the idea was already basically there in conjecture's paper. But whatever. The thought is you give to a GPT-4, like in its prompt, you tell it, here are the words on which this neuron is super activated on. Yeah, so you can visualize this for us with this like color scheme where the greener words are ones on which a neuron is more activated. And you give like a bunch of examples of different pieces of text with these scores of how activated the neuron is by GPT-2. And then GPT-4, seeing all of these, has to come up with an explanation of which words these neurons are activating on. And the explanation it came up with in this example is references to movies, characters, and entertainment.
So in Conjecture's paper, we basically look at a singular direction and then the top K tokens that correspond to this direction, right? Whereas here, we don't look at weights, right? We look at activations. And so we basically look at individual neurons. I don't know whether this is like an MLP, but let's suppose it is. So we like have the residual stream, we multiply it with the input matrix, we apply some nonlinearity, and then we do that for this entire text here, and we see how high the numerical values are at that particular neuron for the entire text. And then we can like overlay this in this like saliency map here and like basically show what this neuron's activation vector values are highest for. And then we like take this data and tell GPT-4 basically, please look at all of these things and tell me what you think the neuron activates on, right?
Mm.
In that sense, the unit of analysis is different because they look at individual neurons and what they pay attention to, but conjecture looked at singular directions in the decomposition of the weight matrices, right?
Yep.
So it's not quite the same.
Yeah,
but the idea, the spirit is similar.
I'm just saying that they're analyzing like a different kind of, somewhat different kind of thing, but the way they're using language models to aid their like to aid the labeling process is very analogous. Like they first have a step where they ask a language model what's in common between all the words, like what explains this neuron's activations, like what's a way to describe which words it gets activated on. And then they also have a verification step after this, analogously to how conjecture has a verification step, though the verification step is a bit more different, I think. So in the verification step, they ask GPT-4 if the explanation was references to movies, characters, and entertainment, which neurons would, like which words would this neuron, which has this explanation, be active on? And then it generates like these activations for this particular neuron. And then you can compare the actual neuron activations, like for this actual neuron, on lots of pieces of text with the fake activations guessed by GPT-4, just having the explanation. And if these match up well, then it sort of means that the explanation was good. Like you can recover from this explanation in words what the neuron is doing. And this is a reasonable standard of you having captured the neuron well, assuming GPT-4 does this well.
Mm-hmm.
So here you can see
some comparisons. Would you be excited about seeing somebody apply like GPT-4 in a manner that OpenAI did here to the singular directions of the weight matrices? Do you think you'd expect like better interpretations of what these clusters are?
Yeah, that's a good thought. I think we probably would get better, like more human-like labeling. I don't know if it would like groundbreakingly change anything, but I could see it like giving higher accuracy, closer to if you actually had humans go through all of this for 330 hours. You'd get closer to those results if you did it with GPT-4. That definitely seems like probably it's true. And I don't know if that would like lead to any qualitative updates though.
Okay, I see. Cool.
Yep. Yeah. So one question I have with these directions is that I'm not sure that they mention in the post that they compared to random directions in embedding space. So if you find that any old direction in embedding space like typically looks pretty human interpretable, then it gives you much less information that you're finding something real about these attention head OV circuits you're analyzing. If like random directions also turned out to be very interpretable, then like it's possible that your interpretability tool is just like picking up some basically random directions that are associated with the OV circuit, but it's not really the case that the OV circuit is like attending to these directions more than to other directions. It's just like you manage to, in some arbitrary way, like pick up some directions associated with the circuit, and like any direction ends up being interpretable anyway. So like, of course, like lots of them are interpretable. I think a good thing, which maybe they did somewhere, but I don't remember right now, or like didn't find it right now, would be to just compare the interpretability scores with random directions. And if you find that like a much larger fraction of the directions are interpretable for model components you analyze than just like random directions you pick, then that's like reasonable evidence that you're doing something real here. Like you're picking up some directions which really the model component is like you're really finding out something about the model, what the model component is doing.
Yeah, I can see. I think even what we would expect, right? Hopefully is, let's say we have a randomly initialized untrained net, and then we just like analyze one of these OV circuits, and then hopefully we just like get gibberish, and that'd be great, because then we know there's something real and like we get somewhere doing training. But to expand on this idea you just proposed, we could also just like add checkpoints, like apply this method and see how the model develops and when it starts to like get these interpretable clusters. And potentially there's like some notion of it getting better and learning something.
That also seems cool. I guess it's sort of hard to say, like, this comparison with random directions might not quite be as strong an update we think it is, because it could just be that there's some like stupid reason why these directions you pick up when you analyze the OV circuit this way are like slightly more pushed towards being interpretable, even though they're not like the real thing, like the real directions, which really like capture what this OV circuit is doing. They might just be like slightly more pushed towards being interpretable than a uniform random direction. And that could also explain a higher fraction being interpretable. So like, even if you do this comparison with random directions experiment, it's like not completely obvious to me that like you have solid evidence that your SVD directions you're finding are capturing some real thing about what this OV circuit is doing.
Yes. How about we wrap up and maybe some like last thoughts? If you had to summarize this paper, what would you say you liked the most here and disliked, and maybe what updated you?
I think it's very cool to have ideas for how to connect weight matrices to some semantic concepts that these particular weight matrices might be looking at. Yeah, especially for the OV circuits, it's quite cool to like be able to understand, oh, this attention head is doing these and these kinds of things. Like it moves this kind of semantic information around. For the MLPs, it's more like it's doing lots of different things, I guess. There's not that many different MLPs as there are different attention heads. But it's still cool to be able to like give some human interpretable labels for these things an MLP is like looking at. So in general, something I'm not super convinced by is like, I think we should try to like understand better whether SVD is the right tool to use, or like in which cases SVD is the right tool to use to find these like interpretable directions corresponding to weight matrices, or also like interpretable directions corresponding to activations. There's also like other options like non-negative matrix factorization, or maybe something completely different. Like maybe we should think about things being more in superposition. Like SVD always gives you, if you have a rank 64 matrix, you're just going to find 64 directions. But maybe it's more like there's actually, in some meaningful sense, like 300 directions in there, and your SVD just cannot pick up 300 things. Like one particular question is, even if there are like at most 64 directions, why do they always have to be orthogonal to each other? SVD always gives orthogonal things, but like maybe models have like other pressures which make directions sometimes be non-orthogonal to each other, like you having to fit lots of things in a small space. And then if you had to have an attention head which attends to some like subset of the things you had to fit in the residual stream, they might not all be orthogonal to each other. So the directions intuitively that the attention head corresponds to, like the OV circuit corresponds to, might not be orthogonal to each other either. And it would just be very nice to have some like more principled understanding of like, why exactly do we expect the directions to be orthogonal, or like maybe we shouldn't expect the directions to be orthogonal, but then like, what do you do if the directions are not orthogonal, even if there's fewer directions than dimension? Like, is there any principled thing you can do instead of SVD? I think that's very interesting, and like if we had a more principled understanding of this, we could maybe make a lot of progress on these decomposing activations into features type questions, but also like finding directions which corresponds to weight matrices. And okay, so that's one thing that is like a criticism, but like also a further direction which I think is exciting. Another further direction which I think is exciting is connecting up our activation feature decomposition stuff with weight matrix, like directions different weight matrices care about, stuff like this work. So can you do some sort of a feature decomposition for like maybe with a sparse sort encoder for language model activations? And can you then see that, oh, actually these same features are attended to by these and these attention heads, and then put together like what the circuits are which compute like from the features in layer L, compute the features in layer L+1 by like understanding which attention heads do which kinds of computations on these features. So I think anything which combines like activation features with attention head and MLP like features that they care about, anything like this would be quite exciting, I think.
Okay, nice, very cool. Thanks for sharing all of your thoughts here with me on this paper. I think this is quite exciting.
Thank you too.